Hello guys, welcome to the lecture series on solar energy fundamentals. This is the second lecture of the series. In this lecture we will learn about the solar geometry. Solar geometry is a spherical coordinate system of the earth that involves the position of the sun in reference to the earth. Solar geometry is always of interest to students because it always allows them to estimate the insolation in kilowatt per square meter and the energy in kilowatt hour per square meter per day at any position on the earth's surface. We already know that knowing the point of intersection of latitude and longitude at that moment allows us to find a location on the earth's surface. Sun is too big and too far away from the earth. The radiation that reaches on earth's surface are assumed to be parallel to each other. To determine the intensity of these incoming insolation on the earth's surface, the following angles must be known: declination angle, latitude, longitude, hour angle, zenith angle, angle of incidence, solar azimuth angle, surface azimuth angle, altitude angle, slope of device. Solar geometry is the study of these angles. Understanding solar geometry requires knowledge of two coordinate systems. The first is known as the earth-centric coordinate system, which helps in defining the declination, latitude, longitude and hour angle. For determining the remaining angle, we must first understand the concept of local centric coordinate system. A 3D spherical shaped wired model of the earth was created in AutoCAD, and the parallel horizontal circular lines on the sphere running east to west represents the latitudes. Latitudes are not simply an imaginary line, but they are coordinates that specify the north-south position of a point on the surface of the earth. These circular lines are positioned across the sphere at the interval of 15 degrees. The circle midway between this sphere represents the 0 degree latitude, which is termed as equator. Parallel circle above the equator in the northern hemisphere represents latitudes and written as 15 degree north, 30 degree north, 45 degree north, 60 degree north, 75 degree north and 90 degree north. And in southern hemisphere, latitudes represents as 15 degree south, 30 degree south, 45 degree south, 60 degree south, 75 degree south and 90 degree south. The sphere's top and bottom points are the north pole and south pole respectively. These points are designated as 90 degree north and 90 degree south, and the vertical lines that emerges from the north pole and merges at the south pole are meridian. Meridians are longitudinal lines on the earth's sphere model. The 0 degree meridian is the prime meridian where world time is determined. As we walk eastward to prime meridian, time increases. As we walk eastward to prime meridian, time increases, where it decreases as we move westward to prime meridian. Similar to the latitudes, longitudes are represented on east and west side of the prime meridian. Eastern side they are designated as E, and on the western side they are designated as W. The line of constant latitudes and longitude together constitute a graticule on the surface on the earth, and these together used as a coordinate pair to specify a location on the surface of the earth. Let us assume a point on the sphere is marked as yellow. This point is the point of the intersection of 30 degree north latitude and 15 degree east longitude. So the coordinate of the points are 30 degree and 15 degree E. So geographically the object is located in northern and eastern hemisphere. The graticules, which is formed by the line of constant latitude and constant longitude on the sphere, are constructed in AutoCAD with reference to the vertical axis, which is a rotation axis of the earth. This rotation axis of the earth is the axis about which earth rotates, intersects the north and south pole and passes through the center of the earth. Suppose this wired model of the earth is turned into a solid sphere and sliced horizontally across the equator into two halves. The lower half of the sphere is displayed here. This horizontal surface is perpendicular to the rotation axis of the earth and circumscribed by a circular line called the equator. So this horizontal surface is known as the equatorial plane. Similarly, the upper half of the sphere is sliced vertically, which is along the axis of Earth rotation. This cut section is known as the meridional plane because its outer surface is bounded by 90° east and 90° west meridional line, and it contains the rotation axis. For more insight, let us slice the upper half of the sphere vertically along the rotation axis and horizontal across the equator and orthogonal to the rotation axis. The cut section of the sphere will look like this. Here the vertical plane is meridional plane and horizontal plane is equatorial plane. An imaginary horizontal line is intersecting at the meeting point of these two hemispheres. This imaginary line is nothing but the equator, so this imaginary line is called as equatorial axis. With the understanding of the concept of the equatorial and meridional plane, let us try to construct the Earth-centric coordinate system. Let us chop off the quarter of the right upper half of the sphere and the vertical line passing through the center of the Earth and both north and south pole is called polar axis. In the chopped portion, the left vertical plane is an arc of meridional plane. The upper part of the meridional plane is touching the polar axis at north pole. The horizontal line emerging from the center of the Earth and orthogonal to the polar axis and extended to both sides, that is south and north, and intersect the meridional plane bounded by the semicircle of prime meridian on one side and international date line on the other side is termed as the meridional axis. Another horizontal line which is orthogonal to both polar axis and meridional axis emerging from the Earth center and extended to both sides, that is east and west of meridional axis and intersecting the 180° E meridian and 180° W meridian at equatorial plane, and let us name it as a equatorial axis. The Earth-centric coordinate system comprises of these three coordinate axes, that is polar axis, meridional axis and equatorial axis, with the origin positioned at the Earth center as seen in the chopped portion. These are the axes of our interest. Another angles are the latitude and longitudes. The latitude of the location on the Earth surface is the angle made by the radial line emerging from the center of the Earth and its projection on the equatorial plane. It is represented by the Greek letter phi. Whereas the longitude of the location on the Earth's surface is the angle subtended between the two meridional plane and is represented by Greek letter gamma as seen in the chopped portion. The angle of incidence is very important as it defines the sun's position with respect to Earth's latitude during any time of the year. Now you recall, in previous lecture we have discussed that when Earth revolves around the sun, then due to its inclination we observe the two solstices and two equinox position. During the summer solstice, that is on June 21, the sun is positioned at Tropic of Cancer, and during the winter solstice, that is on December 22, the sun is positioned at Tropic of Capricorn. Where during the equinox, position of the sun is at equator, that is on March 21st and September 23. It means sun position is changing between the Tropic of Cancer and Tropic of Capricorn, and this angle of declination help us to locate the sun position on any day of the year. Angle of declination varies from maximum and minimum value of plus 23.45 and minus 23.45, representing the sun position at Tropic of Cancer on June 21 and Tropic of Capricorn on December 21 respectively. Mathematically, it can be expressed as delta equal to 23.45 sine of 360 within bracket 284 plus 9 divided by 365. In this formula, n is any Julian day of the year. Julian day of the year means we have to start from the January 1st. On any day, if we are interested in to calculate the angle of declination, suppose we are interested in to calculate the sun position on 5th of February, then we have to take the 31 days of the January and 5 days of February makes the 36. So n value will come out to be 36. Now let us assume that the sun is a point at distant position and a single ray emerging from its center and join the center of the earth. This ray represents the incident radiation from the sun. We can call it insolation also. The angle subtended between the line of insolation and its projection on the equatorial plane is called as angle of declination. As shown in the figure, in the summer solstice, that is on June 21, sun insolations are directly falling on the Tropic of Cancer, that is at 23.45 degree in the northern hemisphere. That is why angle of declination is considered as plus 23.45 degree as per the sign convention. During the spring equinox, that is on March 22, and fall equinox, that is on September 21, the solar insolations are directly falling on the equator, and hence the angle of declination is considered as 0 degree. During winter solstice, that is on December 21, the solar insolations are directly falling on the Tropic of Capricorn in the northern hemisphere, and hence the angle of declination is minus 23.45 degree. The yearly variation in the value of declination is shown in the graph. As we discussed earlier, the same position on the June 21 and December 22 are the position when the angle of declination is plus 23.45 degree and minus 23.45 degree is shown. While during the September 23, the sun is at the equator, that is at 0 degree. Angle of declination is same at all locations on the earth surface on any given day of the year. Only difference is because of the sign convention. If the sun is in the northern hemisphere, then angle of declination is considered as positive, and if the sun is positioned in the northern hemisphere, then angle of declination is considered to be positive, and if it is positioned in the southern hemisphere, then angle of declination is negative.